Okay, let's talk about John Dalton and his model of the atom. So, the model that John Dalton came up with is actually called the billiard ball model. And you might question, what are billiards? They're actually a type of game similar to pool, which is why I've got that on the screen. They're played with the same kind of really heavy, solid balls, and on a table it's felt. You hit them with a cue stick. It's pretty much, basically, if you've ever seen or played pool, then you've seen billiard balls. So Dalton thought atoms were like these billiard balls. They were small, solid, indivisible, with each type of atom being a little bit different in size and in weight. So um, I'm going to go ahead and put this up so that you guys can write down your notes. And then I'm going to kind of explain a little bit. So you can pause the video, write this down, and then go ahead and play it again when you're ready. So I want you to think back to Democritus and his model. Remember, Democritus believed that atoms were tiny, indivisible particles. But his ideas were more like guesses because he didn't have any experiments or technology to prove it. Fast forward 2,000 years to the early 1800s when Dalton was working. By this time, scientists had made huge advances in chemistry, and they were able to measure how each element combined in specific ratios. So, this new knowledge helped Dalton propose a more scientific model of the atom. It's still not 100% correct. I'm a little concerned, talking to a couple of you guys as we were going over vocabulary yesterday. Some of you guys think that the atoms that they're talking about in with Democritus is correct. It's not. We don't have, these are not 100% correct. However, each time a new scientist proposed a new model, it was because they had discovered something to sort of give us more information. So, Dalton says atoms are solid spheres and they cannot be divided anymore. That's wrong. We know that now. At the time, we didn't, but we know that now. However, his second piece of information that he discovered was that each element had a specific size and weight, and that always stayed the same. And he's absolutely right about that. I want you to take a minute, if you would, and turn to page 9 and 10 in your books. Go ahead and do it. I want you to look. Actually, you know what? This is sort of really, I didn't plan on doing this, so forgive me. I'm just going to grab something off. I'm going to grab something very quickly. Here we go. I'm getting this one. Yeah, this is great. All right, so I'm just going to zoom in here so you can see. Well, you can't really. That stinks. Let me see this. See if I can zoom in. Great. All right, if you look at your periodic table of elements in your notes, you're going to see that hydrogen is all the way up at the very, very, very top, and it has a number in the box. Now, this one may look a little bit different than the one that you're looking at, and that's totally fine. The information is probably still the same. It just may be in a different location. But you'll see always at the top a number. And so hydrogen is number 1. And you won't see number 2 until you go all the way over to the right to helium. And that's number 2. And then you have to start all the way. It's like reading top to bottom, left to right. This row, the top row, goes 1, 2, helium, hydrogen. And then you go lithium, barium, boron, carbon, nitrogen. Do you see where it goes 3, 4, 5, 6? We're going to talk more about what those numbers mean. But for right now, I want you to know is that those numbers mean that as we go across the periodic table from the top left to the bottom right, those numbers are going to increase because the atoms are actually getting bigger. They're increasing in weight as they go across the periodic table. So of the 2 points that John Dalton makes with his periodic or with his atom model, one is correct, and it's the last one. Now, let's talk about the differences between. No, I don't need to do that. Got that. Okay. Sorry, I lost my plates in my notes. So now let's visualize Dalton's atoms. And I'm going to have you guys go ahead and draw these out. His image here, like example, would be 3 different atoms. So you're going to go ahead and draw the hydrogen atom, oxygen atom, and carbon atom. And what Dalton did is, in order to represent the differences made that each atom possess, whether it's like a different weight or whatever, he used color to help separate the atoms. So in other words, hydrogen's white, oxygen's red, carbon's black, and for every single one of the periodic table, or every one of the elements on the periodic table, they're going to have a different color. This is something that has continued even to today, this representation of atoms by using color. So Dalton's model may seem simple, and it is, but we're still using it when modeling chemical compositions. Why? Let me show you why. This is a model of a molecule. So each one of those spheres that's colored represents an atom. And you can see from the key there in the top right, you've got a molecule that has 6 carbons in it, 12 hydrogens, and 6 oxygens. This is actually one molecule. All these atoms have to join together. Those little sticks, those represent the bonds that are holding the atoms together. And so this is called a molecule. And this model is a molecule of a substance called glucose. And you may have heard of glucose. It's a type of sugar. Glucose is what plants make when they undergo photosynthesis to feed themselves. If you know anybody who is diabetic, they may have trouble regulating their glucose levels. So this is what glucose looks like. So here's the thing. Why do we still use the billiard ball models when we're talking about complex topics like how atoms are bonded to each other to make molecules, something that Dalton had no idea even existed? The reason why is because it's really simple, because it's really easy to visualize how these atoms are coming together and bonding together to make this molecule. You can't just throw atoms together any old way either. They have to actually bond with each other in a specific reoccurring structure. So every single molecule of glucose is arranged exactly like this. If it's not, then it's not glucose. Okay? So when you are in chemistry class, or I've got some of these. They're little plastic spheres, and those white kind of lines, those rods, they're little plastic. It's like Legos kind of, where you can just kind of snap these things together. And it's not, it's to help you visualize what they look like. So Dalton, actually, we were really thankful to him, because even though we know atoms are more complex than what he thought, Dalton's model is still a really helpful way to visualize them. Okay, so that's Dalton. You've got everything written down on your notes that you need. And so let's go ahead and talk about J.J. Thomson's plum pudding.